This is ELEC 120, and this is the class that comes after ELEC 110. Anybody want to take a wild guess what comes after ELEC 120? ELEC 130. And most likely in the fall you'll have, when you take that class, it will be taught by my esteemed colleague, Mr. Peter Welty. And when you get there, it's a whole new ball of wax. The neat thing about ELEC 120, it's the second half of ELEC 110 as far as the book goes. So between ELEC 110 and ELEC 120, you're going to have experienced a journey from the fundamental physics of electricity all the way through how microcomputers are basically put together from a functional block diagram, which is actually pretty exciting. To reiterate, ELEC 110 and ELEC 120 are survey classes. So this is not designed to make you an expert electronics technician. It's not even designed to make you really an electronics technician. It's to give you a survey, an overview of the entire field that you're embarking on and all the parts that make that up. One of the things to keep in mind is electronics is very much like an onion. It's like an onion. You pull one layer off, and what's below that next layer? Another layer of onion. It's not like a cucumber or an apple. If you peel an apple, outside the peel, the center is the apple. And as you dig deeper, 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 it's all apple. An onion, it's different layers, very much like electronics. So what this is the first layer, an overview, okay? You could dig in ELEC 130, Peter's class, and dig deeper. You could attend the University of Washington, take theoretical classes, get deeper. You could become a PhD and get deeper and deeper and deeper and deeper. The only problem with this industry is as we dig deeper, it continues to grow. So I think if you dedicated your life to getting to the core, you'd never be successful. So, with that being said, let's go ahead and get started here. For those of you at home following along in the textbook, this brings us to section 3 of the book, Semiconductor Devices. And to give you a little bit of background on this stuff, this is actually kind of a cool area. I look back, my dad is 87 years old, he's a World War II veteran, he's still alive, lives in Connecticut, he's quite healthy. When he was a young boy, when he was a soldier in World War II, this stuff hadn't even been invented yet. It didn't even exist. Back in the day, the way it was all done, and some of you may be familiar with this, it was all done with tubes, vacuum tubes. And the catalyst for this development really was World War II. To kind of refresh some of you, there was a guy by the name of Adolf Hitler, right? And he basically wanted to wipe out a whole bunch of people and do some crazy stuff. So we didn't think it was really cool. So we went over there to bomb him and his people into oblivion. Him and his people didn't think that was cool, so they shot back. So when they shot back, these bombers that contained sophisticated electronic equipment, but it was made of vacuum tubes, didn't react well to explosions outside the aircraft. The tubes would break, the electronics gear wouldn't work. So there was a high demand for the development of something that could control current, control electricity, that was in a solid state. So goes the development of semiconductor materials and semiconductor devices. So that's a whole section that we're embarking on. So for old timers, for grandmas and grandpas, great-great-grandmas and grandpas, this stuff didn't even exist. Didn't even exist back in the day. Once the stuff was developed, the growth has been exponential, and it continues to this day. Chapter 19, Semiconductor Fundamentals. After completing this chapter, you, the student, are going to be able to identify materials that act as semiconductors. You're going to be able to define covalent bonding. You're going to be able to describe the doping process. This is different than the doping process that some of you may already be aware of. Describe the doping process for creating N and P-type semiconductor materials. Explain how doping supports current flow in a semiconductor material. Identify the advantages of semiconductors. Identify the disadvantages, because there are some disadvantages of semiconductors. First of all, this is a refresher for those of you that took ELEC 110, which should be everybody in here because it's a prerequisite for ELEC 120, right? Was everybody successful in passing that? I have to go check my grade books. Keelan, are you passed? I don't think so. Anyway, you all remember in our first lecture in ELEC 110 we talked about materials? And we've got really four different materials that I mentioned. The primary three materials we talked about are conductors, insulators, semiconductors, and what was the fourth I talked about? Superconductors. Very good. So we've really got those four materials that are used in industry right now. Well, superconductors really aren't used in industry that much. They are used in some applications, but they're not really prevalent because it's very difficult to work with those materials. Anyway, back to the basics. 3 electrons or fewer in the valence shell makes it a good conductor. 5 or more makes it a good insulator. What number? I'm thinking of a number between 3 and 5. 4. It's amazing. It's uncanny. Mathematician. 4 electrons in the valence shell makes it a good semiconductor. And I think that, don't you wish that you lived back in World War II and were like a scientist? Because you could have drawn that same conclusion. You know, we're looking for a number between 3 and 5. 4. Let's look at those materials. And that's what they looked at, were those materials. And what we came up with, what they came up with, was carbon, germanium, and silicon. Those 3 materials. They said they have 4 electrons in a valence shell. We'll see if we could play with them so that they begin to act like a semiconductor. The first material that we're going to discuss is germanium. This is germanium, not geranium. Geraniums grow in flower boxes. I think they like lots of sun and water. I'm sure a lot of you are shocked that I even know that. Actually, I kind of made it up, but I think it's the truth. Discovered in 1886. Recovered from the ashes of certain types of coal. Don't ask me how they discovered it in 1886 and like, well, you know, they're going through ashes of coal. Oh, wow, look at this. It looks like germanium. Germanium, not geranium. When it's reduced to a solid form, you end up with pure germanium. Silicon, discovered in 1823, found in the Earth's crust as silicon dioxide. It's white or sometimes colorless, abundantly found in sand, quartz, agate, and flint. Chemically reduced to a pure silicon in solid form. And it is the most commonly used semiconductor material. Where does most of our silicon come from? What region of the world? Anybody know? Anybody here heard of Silicon Valley? Have any of you been to Silicon Valley? What's there? Vast mountains, sand dunes of silicon? What's there? If you went to Silicon Valley, what would you see today? Lots of buildings. Lots of high-tech buildings. The reason Silicon Valley is called Silicon Valley, it's where a lot of the developmental work did in harnessing the material silicon for electronic use. And it's located basically down in the San Jose area of California, just south of San Francisco, Silicon Valley. One of my favorite James Bond movies of all time, A View to a Kill. Remember that one? Zorin Industries with the Zeppelin, the blimp. Christopher Walken as the madman. I mean, it doesn't get any better than Christopher Walken as a madman. And what he was going to do is, I don't know, create an earthquake in the San Andreas Fault and flood Silicon Valley because he held, you know, all of the world's microchips. And anyway, great movie, highly recommend it. They talk about Silicon Valley. The big thing that we got to look at here is the subatomic structure. You're all familiar with the valence shell, the outermost shell. Here are 4 electrons orbiting the nucleus of the valence shell. That's what makes this a good choice to use as a solid-state semiconductor material. Now, in this particular case, we're talking about silicon atoms. Now, we need to grow these silicon crystals. Have any of you here ever grown crystals before? What kind of crystals did you grow? In a box? You know what kind they were? I heard somebody say rock candy. Rock candy, which is nothing more than basically melting sugar in water, and then as the water evaporates, the sugar starts to crystallize. You put a string in there, the crystals cling to the string, and then you have rock candy. That's nothing more than pure sugar, but it's sugar crystals. You do the same thing with salt. They do the same thing with silicon. They have a seed, which is a perfectly pure form of silicon, and then what they do in molten silicon is basically, it's almost like dipping a wick for creating a candle. It's very similar, that it crystallizes on it. And as long as this is done in a perfectly clean environment, you end up with pure silicon, intrinsic silicon. And when you grow it together as a crystal, you develop what's called this covalent bonding. Covalent bonding. It's the process of sharing valence electrons resulting in the formation of crystals. So those of you in the back of the room have the best view of this. If you actually look at this, you see how it's all laid out in like a geometric pattern here? That's because that outer valence shell is sharing the orbit with the one next to it, and you create this covalent bond. So the manufacturing process is very, very critical. All of this has to be done in a clean room. A speck of dandruff, a speck of dirt, a speck of dust means it's going to be embedded in this material, and you won't have that covalent bond. So you want to get this as pure can be. One of the things that you need to understand about these semiconductor materials is their behavior as it relates to temperature. Those of you that completed ELEC 110 shouldn't be surprised. Temperature does affect resistance, does it not? And with a conductor, how does that work? When the temperature increases, the resistance goes up. Which, if you're an extension cord that's starting to get warm, is a bad thing, right? Because the hotter the extension cord gets, the more resistance, the hotter it gets, the more resistance. Next thing you know, what's that? That's burning. Holy crap. My extension cord's on fire. So that's a problem. Negative temperature coefficient is the opposite. As the temperature increases, resistance decreases. So we could say there's an inverse proportional relationship. That means it's a negative temperature coefficient. This is going to be the behavior of semiconductor materials. Now for silicon, which is again the most popular semiconductor material, resistance is cut in half every 6 degrees Celsius of rise in temperature. So you rise 6 degrees in temperature, whatever resistance you're at is now cut in half. For germanium, resistance is cut in half for every 10 degrees Celsius of rise in temperature. So it takes a bigger change in temperature to bring that about in germanium. Does temperature affect semiconductor materials? What's the most important thing to remember then when working with semiconductor materials? Maintaining the proper temperature. You folks have all heard about my background right? I've shared with you my background, my military background. You know the most important job I ever had, other than teaching all of you fine people? Probably the most important job I ever had was when I was a very junior technician on board a nuclear submarine. And one of the things that I had to do on a weekly basis was pull out air filters out of our equipment racks and vacuum those air filters. Then reinstall them. Once a month, I had to put it in a ultrasonic cleaner. Vacuum them, put it in an ultrasonic cleaner, and then put it back in. There were weekly maintenance procedures or monthly maintenance procedures. Why was that such an important job? What effect would it have had if I decided to blow off my responsibilities?
What was the filter?
It was an air filter going to electronic equipment racks. Just a simple air filter, like the air filter in your furnace at home.
So they're clogged up with the heat bill?
Absolutely. If I blew off my job and didn't vacuum them out, there wouldn't be sufficient airflow. If there wasn't sufficient airflow, it would have overheated the equipment and the equipment would have failed. So literally, a multi-billion-dollar submarine on a mission somewhere on the other side of the world could have been compromised because I decided I wasn't in the mood of vacuuming out the air filters. And I'm not over-exaggerating. It's that critical. One of the things that I do at home is twice a year. I typically take my computer, my PC, I take the cover off, I bring it outside. At home I have an air compressor. I make sure that the case is grounded, because those of you that are embarking on static understanding of static electricity, air flowing past a circuit could generate static electricity. So I make sure the case is grounded, and then I blow it out with high pressure air. And I'll be honest with you, it's kind of embarrassing when I do it. It's like a cloud of freaking, you know, what was it, Peanuts there, Pigpen? Wherever he walked around, it's like a cloud following him. So my neighbors go by, what the heck's he doing? There's all this dust. That's all dust that's in my house. But it likes to collect on the circuit board. When it gets into the circuit board on the computer, what does it form? It forms like a blanket over the electronic components. So the heat can't be dissipated, and the computer is going to be much more prone to failure. The same thing with all your electronic equipment. Amplifiers. I just did that with my DirecTV, my TiVo unit. About a month ago, I was in there, opened it up, brought it outside, blasted it all out. It looks as good as it does the day it was manufactured. Okay, so you want to get dust out, because this stuff, the semiconductor materials, are affected greatly by a change in temperature. Silicon has 1,000 times more resistance than germanium at room temperature, thus making it more stable. Germanium is used where heat-sensitive applications are necessary. And today, silicon is used for most solid-state applications. Silicon is really the big material that's used out there. That's why there's Silicon Valley. Have any of you ever heard of Germanium Valley? Or Carbon Valley? Carbonado, down by Mount Rainier. That's a little bit different, though. Conduction in pure germanium and silicon. Let's talk about conduction in these two pure materials. Electrical activity is highly dependent on temperature. Let me say that again, this time real slow. Electrical activity is highly dependent on temperature. Germanium and silicon crystals function as insulators at low temperatures. So at an extremely low temperature, they're like insulators. As the temperature rises, they begin to acquire the characteristics of a conductor. So if you've got pure germanium and silicon inside a box that you can control the temperature of, just by you changing the temperature is going to change the amount of resistance in the material. That's what's key. Does that make sense? Now, here's something that I didn't want you to talk about in ELEC 110, Now we're going to talk about it in ELEC 120. Hole. Hole. An all-female progressive rock band from Seattle, Washington. Hole. Was it Beavis and Butthead Do America? There's reference to that, isn't it? Because they're talking about going to Washington. Any of you see that movie? Right? What was the whole premise of that? Someone like stole their TV or something, or they stole the TV from the school and we're going to find a TV, or they're trying to get a TV. So they're going to go to Washington, right? And they were talking about Washington, D.C. This bus is going to Washington. Cool. Is it Seattle and Washington? We could go see Hole. Has nothing to do with this, but it's actually somewhat entertaining. Anyway, that's not the Hole we're talking about here. We're not talking about the female progressive rock band from Seattle. We're talking about the absence of an electron. Now, how do we create an absence of an electron? The process is called, well, here it's called doping, but up to this point, wasn't it ionization? If we apply energy to matter, we could knock an electron off. Off what? Off the valence shell. If we knock an electron off the valence shell, that means we're left with a positive ion. Positive ion means there's an absence of an electron. The absence of an electron here in our discussion will be signified as a hole. So what it does is it represents the loss of a negative charge. Therefore, it has the characteristic of a positively charged particle. Now, each corresponding electron and hole are referred to as an electron-hole pair. Because you remember my lectures in the past, in the beginning, everything was in a neutral natural state. That means there's an equal number of electrons and an equal number of protons, so all atoms are in a neutral natural state. And it will remain so until we impart energy on matter. Question?
Yeah, if an electron is a particle that actually has some mass, even though it's very, very minuscule.
Yes.
Is a hole actually considered to be something that has mass since it's defined as a particle, like an electron, or is it more of a complementary state?
More of a complementary state, because that absence of the electron mass-wise is pretty insignificant. Now, holes constantly drift toward the negative terminal of a voltage source. Why would a hole constantly drift towards the negative terminal of a voltage source? Opposites attract. It's that simple. Because opposites attract. If you're a hole, you want to be filled by what? An electron. Where do electrons hang out? The negative terminal of the voltage source. If you're an electron, what do you want to do? Fill a hole. What are your best chances of filling a hole? By hanging out on the negative terminal as the holes are attracted to you. Does that make sense? So this is just, it's a fundamental physics property of this drift that's going to take place. Now, electrons flow towards the positive terminal because they want to fill the holes. Now, current flow in a semiconductor consists of the movement of both electrons and holes. Everything you studied up to this point in ELEC 110, we were only really concerned about current, I. 1 amp is equal to 1 coulomb per second. Remember that? Now, to be totally honest with you, whether 6.24 times 10 to the 18 electrons go this way per second, or 6.24 times 10 to the 18th holes go this way per second, either will equal 1 amp. Does that make sense? So don't be confused by holes. We didn't want to beat it to death in ELEC 110, but I want you have to understand the concept of a hole, the absence of the electron. Make sense? Can you dig it? So as I just stated, the amount of current flow is determined by the number of electron hole pairs. 6.24 times 10 to the 18th electrons this way per second, 1 amp. 6.24 times 10 to the 18th holes per second, 1 amp. It's the same. Electron hole pairs. The ability to support current flow increases with the temperature of the material. Because as the temperature rises, the resistance drops. And that's actually a problem for some electronic systems, right? Because as the temperature increases, all of a sudden current wants to flow more. Maybe more than should be flowing. And that's what may cause a solid state component to fail. Direct result of a change in temperature. Fail. Now, just having the solid state, pure solid state materials really don't do a whole lot for us. So what we need to do is we need to increase the conductivity of the semiconductors. This is done through a process called doping. So you all get to go home tonight and what are you learning over there at that college? Oh, my teacher is teaching us about doping. You know, and that's part of the whole college experience, right? Actually, what we're talking about is a little bit different. But still doping. Doping is the process of adding impurities to a semiconductor material. Not just adding impurities for the sake of adding impurities, but adding specific impurities to change their behavior. Now, we're going to really use two different classes of materials as dopants. One of the classes is going to be called a pentavalent dopant, and the other is going to be called a trivalent dopant. Now, pentavalent, penta means 5, like a pentagram, penta meaning 5. You got a pentagram on your hand? There you go. Permanently? No. You thinking about it? You just doing a dry run? All right. I was thinking I got one for my forehead. Your shocking experience. Now, pentavalent made of atoms with 5 valence electrons. The two primary materials that are used in the industry are arsenic. That's fun stuff to, you know, break out at parties, all right? Arsenic and antimony. Arsenic and antimony. The trivalent dopants have 3 electrons in the valence shell. And this includes indium and gallium. Indium and gallium. What we did here is we got pure silicon. Pure silicon in a molten state. Got one of those ladles stirring the soup. And then what we got is a pinch of arsenic, and we added a pinch of arsenic to our silicon. And then what we did is we grew it into a crystalline structure. No longer pure. Now we have a dopant, arsenic, introduced into it. When we begin to grow the crystals, the arsenic atom will develop a covalent bond with the silicon atoms, thus growing it into the material. So it becomes part of the permanent material, grown right in, part of the crystalline structure. Does that make sense? It's pretty crazy how they thought this stuff up. It works. In doing so, we have just created what is known as an N-type material. An N-type material. It has more electrons than holes. Why does it have more electrons than holes? It has more electrons than holes. Let me go back a slide here. Because arsenic is a pentavalent material, and we grew it in here. So we grew in an atom that's got an extra electron in its valence shell. Now it's sharing the orbit, if you will, with the adjoining silicon atoms, and it's grown right into the crystalline structure. So we're going to say that it has more electrons than holes. Negative charge is going to be what we call the majority carrier. Now this slide alone is probably about 15 different ways I could ask you questions from this slide. If negative charge is the majority carrier, what's going to be the minority carrier? Positive. Thank you. Positive. I always used to get these questions wrong when I was a student. You know, negative charge is the majority carrier. What is the minority carrier? Arsenic? You know? It's like, no. We're talking about charge characteristics. So how many charge characteristics do you know about? Honestly. What are they? Positive, negative, and neutral, right?
Neutral's not a charge state, though.
But we could consider it a characteristic, can't we? A neutral charge. That means there's an equal number of positives and negatives, so we could stretch it to that.
Good point. They're complementary.
Yeah. So again, look for stuff like that on my quizzes. And I'm not trying to trip you up. I'm just trying to prepare you for industry exams that are going to really make sure you got a grasp of this stuff. Because we no longer are studying the history of electronics. You know who plays with this stuff on a daily basis? A company called Intel, because this is how they make their microprocessors. These are the materials that they use. A company called Motorola, right? The microprocessors they manufacture, this is what they manufacture them out of. So this is no longer the history of electronics. This is what's really going down. So in an N-type material, what we're looking at here is a series circuit. Here's our voltage source. This is N-type material. And what's going to happen is electrons are going to want to flow through this material. And the majority carriers are going to be these electrons. Why? There's more grown in. Where did they come from? We grew them in the doping process by adding a pinch of a pentavalent dopant. Make sense? Can you dig it? You have a question. What is the question? No. And to be honest with you, but no and yes. When scientists beat their head against the wall trying to figure this stuff, these are the materials that they came up with. And quite frankly, I don't know, and I really don't want to know because it never helped me fix a piece of electronic equipment and knowing what the process is. I'm sure you could do some additional reading on the subject, but I don't know what drew the scientists specifically to those materials and what some of the other materials that had pentavalent materials that did not lend themselves well for that use. Good question, but I don't know the answer. Hey, check this out. Indium, that was what type of a dopant? Trivalent, meaning 3 electrons of the valence shell. Same thing. You get your vat of pure silicon, you stir it with your wooden spoon or your ladle or whatever you're doing with it in a clean room. Somehow I don't think you're going to be using a wooden spoon. But then you add a pinch of indium. I've got some of that in my spice cabinet, right? Indium, a pinch of indium. Right? Saffron rice with a pinch of indium. I don't think you want to be adding indium to your rice. When you grow it into a crystalline structure, you grow in a hole. What's the definition of hole? Absence of electron. You folks are like my best ELEC 120 students this quarter, by far. So we grow in an extra hole into the crystalline structure and create this covalent bond. In doing so, we create what's known as a p-type material. P-type material has more holes than electrons. Positive charge is what we call the majority carrier. If positive charge is the majority carrier, what is my minority carrier? Indium. No, what is my minority carrier? It's going to be the electron, right? It's always going to be the opposite. If one is majority, the other is minority. It's that simple. You've only got 2 things, electrons and holes. There's nothing else. No other moving parts. And those parts aren't even really moving, I guess. Maybe they are. I guess in a solid state they are. The holes move towards the negative terminal. Why does this happen? They want to get filled. Holes want to get filled. Electrons want to fill the holes. So in this particular case, that's why they're going to migrate. In summary, semiconductor materials are materials with characteristics that fall between those of insulators and conductors, literally, right? 3 electrons or fewer makes it a good conductor. 5 or more makes it a good insulator. I'm thinking of the number between 3 and 5. 4, 5, 3.2. That'll be a distractor on my quiz. 3.2. I don't know how half the stuff works. Pure semiconductor materials include the use of germanium, which you'll see out in industry. Silicon, absolutely, it's number 1, the most popular. And carbon. I don't even know if in my life, my entire adult life, I've ever even seen carbon. I don't know. Don't know. Couldn't tell you. Beyond the scope. Silicon is used in most semiconductor devices. Valence indicates an atom's ability to gain or lose the electrons. Semiconductor materials have valence shells that are half full. Literally. That way you could add to them or subtract from them by the use of dopants. Covalent bonding occurs when atoms share their valence electrons. And that's how we grow crystals. Heat creates problems by allowing electrons to break their covalent bonds. A hole is the absence of an electron in the valence shell. Current flow consists of both electron flow, right, and hole flow. Doping adds impurities to the mind. No, excuse me. Doping adds impurities to a semiconductor material. The dopants that we use, trivalent materials, have atoms with 3 valence electrons. They're used to make p-type material. Holes are the majority carrier. That makes electrons the minority carrier. Pentavalent materials have 5 valence electrons. They're used to make n-type material. Electrons are the majority carrier. Holes, therefore, are the minority carrier. N and p-type semiconductor materials have a higher conductivity than pure semiconductor material. Remember, that's how we increase the conductivity, by adding that dopant, either trivalent or pentavalent. Anybody have any questions on anything in our first chapter? Okay, let's go ahead and take about a 10-minute break, and shortly after 20 after we will start up with chapter 73, PN junction diodes. I get emotional. It's your first real component. Absolutely. Why not? Absolutely. We'll even do 4 or 5.